In this video, we're going to start chapter 21, and chapter 21 is on nuclear chemistry, which is going to be quite different from what we've been doing. Chemical reactions, remember, are reactions that involve electrons, right? We're breaking bonds, which are electrons. We're rearranging atoms and forming new bonds, which are composed of electrons. Nuclear chemistry is called nuclear chemistry because it's the reaction of the nucleus. So instead of looking at electrons, we're going to be looking at protons and neutrons. So a bit of a departure from what we've been doing. So nuclear chemistry. And then again, by definition, nuclear chemistry is the study of the properties and reactions of atomic nuclei. So just a quick review of our parts of an atom, right? Our nucleus contains protons and neutrons. Outside of our nucleus are our electrons. Chemical reactions, again, essentially involve valence electrons. So in chemical reactions, it doesn't matter which isotope you have, right? If it's carbon-12 or carbon-13, from a chemical standpoint, they're going to behave very similarly. From a nuclear standpoint, they're going to behave differently. So just kind of reviewing a little bit here, I had mentioned carbon-14, carbon-13, and then carbon-12. Right? All of these are carbon atoms, right? We know that because I'm putting down a C, right? Which is the atomic symbol for carbon. If we look up my atomic number, it's going to be 6 for all of these. So isotopes, remember, are atoms of the same element with different mass numbers. Remember, it's the atomic number that defines an atom as belonging to a particular element, right? Writing the C and writing the 6 is redundant. If it didn't have an atomic number of 6, it wouldn't be carbon, and carbon has to have an atomic number of 6. So anytime we write the symbol C down, it's going to have an atomic number of 6 every single time. If it wasn't 6, it's not carbon. It's not carbon if it's not 6, right? My atomic number tells us which type of atom we have. If I was to change that 6 to a 7, I have nitrogen instead of carbon. If I was to change it to a 5, I have boron. So this here was my atomic number. Oftentimes, I don't even write down the atomic number when I'm writing an isotope because, again, this C and this 6 are redundant. If you put the 6 there, you don't really need the C because it's obvious, right? We have a periodic table, it's always carbon. If you put a C here, you don't really have to write down the 6 because we have a periodic table, it always has to be 6. So our atomic number, right, this tells us the number of protons in the atom's nucleus. And again, it defines an atom as belonging to a particular element, sorry. I almost said isotope, as belonging to a particular element. And then, since we just mentioned isotope, we'll reiterate that one. We're going to use isotopes a lot in this chapter. They're atoms of the same element, but my mass number is different. So that was that number up here, right? One of these has a 14, the other has a 13, the other's a 12. So these would be isotopes of each other. They're all carbon atoms, but they have different mass numbers. So this number up top, this is going to be a long arrow. I didn't give myself a lot of room. So this is my mass number. And remember, our mass number tells us the number of particles in our nucleus, so the total. And we know in our nucleus we have protons and neutrons. I know 6 of those 14 particles are protons, so 14 minus 6 is 8. I have 8 neutrons in the nucleus. So this tells us the number of protons, P for protons, and neutrons, N for neutrons, in the nucleus. Essentially, the total number of particles in the nucleus. So if we were to subtract our mass number from our atomic number, we get the number of neutrons. A new term that you might not have heard before, and this does come up in nuclear chemistry a little bit, are nucleons. And a nucleon is just kind of the quick way to say protons plus neutrons. So a nucleon is the number of particles in the nucleus, so the number of protons plus neutrons. So the number of nucleons is going to be equal to my mass number. So this is the number of particles in the nucleus. So it's essentially the number of protons plus the number of neutrons. So if I look at carbon 14, I have 14 nucleons. I have 13 of them in carbon 13. I have 12 in carbon 12. My neutrons, I'm going to take my mass number, which is the number of protons plus neutrons. I'm going to subtract my atomic number from it because that's the number of protons. That's going to leave me with neutrons. So carbon 14 here, right? It has 14 particles in the nucleus, right? 6 of those are protons. So 14 minus 6 gives me my 8 neutrons. Carbon 13, 6 protons, right? If it didn't have 6 protons, it wouldn't be carbon. 13 minus 6 is 7 neutrons. 6 protons again, because it's carbon, has to be 6. And then 12 minus 6 gives me 6 neutrons. So again, my isotopes, right, are all atoms of the same element, so they have to have the same number of protons. If they didn't, they wouldn't be isotopes. And then to make their mass numbers different, it's the number of neutrons that we're varying. So you could rewrite your definition for isotopes if you wanted as atoms that have the same number of protons, right, that makes them the same element or belonging to the same element, but different number of neutrons. We can try to squish it in here, but, right, same number of protons, but a different number of neutrons. And then remember, mass numbers are always going to be whole numbers, right? They're always going to be counting numbers. One of the kind of Ricky mistakes back in 130 or maybe even 151 is to get atomic mass messed up with mass number, right? Atomic mass, we're actually talking about the mass, actually the weighted average mass of all of an atom's naturally occurring isotopes, but kind of like what does it weigh sort of thing. Mass number is a counting number. We can't have fractions of protons or fractions of neutrons. We can always only have whole ones. So these are always going to be whole numbers. Next, I do want to look a little more detail about the differences between nuclear and chemical reactions. So we'll make a list here. Right? I've already mentioned that chemical reactions involve our valence electrons, and nuclear reactions involve our nucleus, but I want to write that down, plus some other differences here. So differences between chemical and nuclear reactions. So our first one, nuclear reactions involve a change in the atomic nucleus. So nuclear reactions involve a change in the atomic nucleus. Often we actually produce a different element. Right? If we're changing the nucleus, we can be changing the number of protons, and when we do that, we actually have an atom of a different element. Remember, if the number of protons change, we're actually making something different. That doesn't happen in chemical reactions. Right? A chemical reaction just involves a change in the distribution of valence electrons. The nucleus itself is not changed. So chemical reactions just involve a change in the distribution of valence electrons. Right? The nucleus itself is not changed. Because of that, number 2, different isotopes are going to behave differently in nuclear reactions. Because their nucleus is different, they're going to behave differently. In chemical reactions, they're going to behave the same because the nucleus is not part of it, right? If we were to go back up here and look at electrons, right? Remember, if our atom is neutral, my number of protons are going to be equal to my number of electrons. So all 3 of these are going to have 6 electrons, right? They have 6 positive charges. My protons have a positive charge. So if they're uncharged, they're going to have the same number of electrons. So if we're talking about reactions that are involving this, they have the same numbers, they're going to behave similarly. If we're talking reactions that involve this, they're different, they're going to behave differently. So number 2, different isotopes behave similarly which I can spell really, in chemical reactions, but differently in nuclear reactions. Third one, changes in temperature, pressure, or the addition of a catalyst do not affect nuclear reactions. They do affect chemical reactions, we know though. So changes in pressure, so P for pressure, temperature, T for temperature, or the addition of a catalyst have no effect on a nuclear reaction. And then the last one, the energy changes for nuclear reactions are often way, way greater than the energy changes for chemical reactions. So the energy changes for nuclear reactions are much greater than those of chemical reactions. So nuclear reactions involve a change in my nucleus, right? That's why they're called nuclear reactions. Chemical reactions, just a redistribution of valence electrons. Because different isotopes have different nuclei, they're going to behave differently for nuclear reactions. Because chemical reactions don't involve the nucleus, different isotopes are going to behave similarly in chemical reactions. Things that usually affect chemical reactions don't affect nuclear reactions, and then our energy changes for nuclear reactions are often much, much greater than those of chemical reactions. Do you want to talk a little bit about nuclear stability? So often in nuclear chemistry, when we use the word stable, we're talking about isotopes whose half-life can be measured. If we say unstable, we're talking about isotopes that decay too rapidly to be measured. So stable, and again, this is in nuclear chemistry. Right, this is going to refer to radioactive isotopes, which we'll talk about here, whose half-lives can be measured, meaning it doesn't decay so fast that we can't measure it. If we say unstable, again, in nuclear chemistry, we're talking about radioactive isotopes whose half-lives can be measured, or sorry, cannot be measured. Right? Unstable, they're decaying so fast we can't measure their half-lives. So essentially, not all nuclei are equally stable. So not all isotopes are equally stable. Carbon-13 and carbon-12 are stable. Carbon-14 is not. So not all nuclei are stable. Ones that are not stable are actually going to decay to form something that is more stable. So that's what when we say radioactive, that's what we're talking about. Radioactive nuclei are nuclei that are going to emit radiation, sometimes actually absorb, we'll talk about those. So emit and absorb radiation to become more stable. And we'll talk about what that radiation is. So not all nuclei isotopes are stable. Radioactive isotopes or nuclei, you could swap out either word here, will emit or absorb radiation to become more stable. Right? Things still want to be stable, just like in chemical reactions, right? Stability is our goal. If it's not stable, it's going to do something to become more stable. In this case, it's going to either emit radiation, it's going to decay in some way, or it's going to absorb something to become more stable. So kind of the carbon-14 example. Carbon-14 is not stable. I'm going to put my atomic number here, and what it's going to do is it's going to emit, this is a beta particle, and we'll make a list of all types of radiation, but it's going to emit a beta particle and actually form nitrogen. And nitrogen-14 is relatively stable. So radiation types, right? Common ways are nuclei can decay to become something that's more stable. And our first one is an alpha particle. So we could say alpha emission, alpha decay, alpha radiation, all of those terms work here. And our symbol is a Greek letter alpha. And what an alpha particle is kind of a stream of particles that contains 2 protons and 2 neutrons, which is essentially the nucleus of helium. So sometimes an alpha particle is just called a helium nucleus, because if you were to look at the nucleus of helium, right, it contains 2 protons and 2 neutrons. It's most common isotope, so helium-4, I should specify. So consists of 2 protons plus 2 neutrons. So all 4 of those particles is my alpha particle, right? It's essentially a helium-4 nucleus. It has a positive 4 charge, right? Whoa, sorry, has a positive 2 charge, right? It has 2 protons. Protons have a +1 charge each, so it has a positive 2 charge. Our symbol, we're going to balance reactions here in a little bit, so we need a symbol for it. So often we'll actually just use helium and then the 4 and the 2. So again, remember, this is my, right, atomic number, so that's the number of protons, so 2 protons. And then this 4 is the number of protons plus neutrons, so that's 4. Sometimes it is written using the alpha symbol with a 4 and a 2, so that's perfectly acceptable also. I tend to write it this way, but you may see this. And when our nucleus emits an alpha particle, its mass number is going to be decreased by 4, and then its atomic number is going to be decreased by 2. So the mass number, this is after it emits it, is decreased by 4, and the atomic number is decreased by 2. So looking at an example here, I'm going to have uranium-238. And we're going to balance this one. I'll write down the rules for balancing them here in a minute. But often when I give them to you, I will just give it to you like this. I won't actually write the atomic number on there because you can use your periodic table to look up the atomic number. You are going to need that. So find uranium on your periodic table, look at its atomic number, and then do add that. So again, if I don't have this atomic number here, we do need it, so please just look it up on your periodic table. Just find U, right? All atoms of that element are going to have 92 as their atomic number. And then in this example, it's emitting an alpha particle. So over here as a product, right, it's giving it off, I'm going to draw my alpha particle. And then what we need to do is we need to write the atom that results, or the nucleus that results from that. So when balancing nuclear reactions, which is what we're doing here, we can't balance atoms anymore, right? Remember, oftentimes sorry, I should say that differently. We can't balance elements anymore, right? Often we're producing different elements. What we're going to do is we're going to balance protons and neutrons. So instead of conserving atoms, we're conserving subatomic particles. So protons and neutrons are conserved. If you think about chemical reactions, right, is breaking bonds, rearranging atoms, and then reconnecting them. Essentially, we're redistributing electrons. Here, you can kind of almost think about it as redistributing our subatomic particles, right, redistributing our protons and our neutrons. So I'm not going to necessarily have uranium on both sides, but I need to have the same number of protons and neutrons on both sides. So essentially, the sum of my atomic numbers need to be equal on both sides of my equation. And then the sum of the mass numbers must also be equal. So if we go back up and look at that carbon one that I did. So here I have a 14. Here I have a 0 and a 14. So I have a sum of 14 for my atomic numbers on both sides. Here I have a 6. Here I have a -1 and a 7. -1 plus 7 is a 6. So the sum of atomic numbers is the same on both sides. And that's what we're looking to do. So when we're balancing this one, right? I know that my mass number, sorry, my atomic number, we want to do that one first. I guess it doesn't really matter, but I like to do that one first, right? My atomic number is decreased by 2. The other way you can look at it is I have a 92 here, here I have a 2. To make that sum equal, I have to have a 90 here, right? Because 90 plus 2 equals 92, and I need my sum of my atomic numbers to be equal. I'm then going to look at the periodic table. I'm going to find 90 on the periodic table, and then I'm going to write down that symbol. So in this case, TH, right? That's the one we're matching to 90. And then for my mass number, this is a 238, this is a 4. 238 minus 4 gives me a 234, right? Again, 234 plus 4 equals 238. The sum of my mass numbers has to be the same on both sides of the equation. My second type of particle is a beta particle. Greek symbol or Greek letter beta. Sometimes this one is actually written the beta symbol with a minus. That'll kind of make more sense once we do one of our other types of radiation, but I'm more commonly am just going to write it without the negative, so just the beta. But again, if you see the negative, it is the same as the symbol without the negative. And with this one, what's going to happen is a neutron in the nucleus actually decays into a proton and an electron. And then electrons have no business being in the nucleus, so it's ejected from that nucleus. So that electron that we're ejecting from the nucleus is my alpha particle. So a neutron in the nucleus decays into a proton and an electron. And then that electron is ejected from the nucleus. So essentially what a beta particle is, it's an electron that's actually coming from the nucleus when our proton decays, when a neutron decays into a proton plus an electron. So I have a neutron in the nucleus, and then writing its symbol down here where I would normally have a my atomic number, I'm going to put a 0, right? Neutrons don't contribute to my atomic number, so I'm going to put a 0 there. And then it does have a mass for its mass number 1 because I have 1 neutron. And then it's decaying into a proton. Here I'm going to put a 1 and then also a 1 in my mass number, right? I have 1 proton, so my atomic number is 1 because that's the number of protons. And then my mass number is protons plus neutrons. And then my symbol for my electron, I'm going to do an E. And then I'm going to put a -1 here where my atomic number would be, right? Remember, the charge on my electron has the same magnitude but the opposite sign as a proton. So instead of being a +1, it's a -1. And then electrons don't contribute to the mass number, so we put a 0 up there. And then if we look at this, it actually is balanced, right? Here I have a 1 and a -1, which sums to 0. Here I have a 0 and a 1, which sums to 1. The mass of a neutron and the mass of a proton are very, very similar. Remember, the mass of an electron is much, much lighter and often considered negligible. So this happens, right? This neutron, right, is decaying into a proton plus an electron. This electron then has no business being in the nucleus, so it's kicked out, it's ejected from it. So this here is my beta particle. So it has a -1 charge. And then our symbol when we're balancing it is going to be this. Sometimes the Greek letter beta is used. So if you see that, that's fine also. I do typically use the E for the electron, but again, if you're looking up other sources, you may see that also. So an example for this one, we already did the one with carbon, but we'll do another. So I have iodide 131. And again, if I don't give you the atomic number, just find iodide in the periodic table. It corresponds to an atomic number of 53. And then it's going to eject a beta particle. So I'm going to write my symbol for the beta particle. And then we need to determine what my new isotope, what my new nucleus is. So again, remember, we're going to conserve our atomic numbers, right? The sum of the atomic numbers must be the same on both sides. The sum of my mass numbers must be the same on both sides. So if this is a 53 and this is a -1, this one is going to have to be a 54, right? 54 plus a -1 equals 53. And then find 54 on the periodic table, write down its symbol, so xenon. And then 131 minus 0 is 131. So this time, my mass number doesn't change. We can actually write this down. The mass number doesn't change. But the atomic number, which is N, the atomic number, increases by 1 when a beta particle is ejected. Our third type is gamma radiation. This one we're not going to call a particle. So with alpha and beta, I could say alpha radiation, I could say an alpha particle, I could say it underwent alpha decay, alpha emission, any of those things worked. Here we can't use the word particle. It's actually not a particle. Gamma radiation doesn't have mass, and we're going to define particles as things that have mass. Sorry about that. So our gamma particle Greek letter for gamma. And let's actually write that down in parentheses so we remember not to call it a particle. So what this is just essentially high energy electromagnetic radiation. If you remember the electromagnetic spectrum from 151, we had radio waves at one end, right? They had the biggest wavelength, the smaller frequency, and the smaller energy. And then at the far other end, we had gamma radiation. They had the smallest wavelength, the largest frequency, and the largest energy. So has no mass or charge. And it's essentially just a stream of high energy electromagnetic radiation. So essentially we're just giving off energy. Our mass number and our atomic number are not changing. If we did want a symbol for it, we would actually put a 0 where both the mass number and the atomic number go. If you were to balance reactions with it, then we're not going to have a change, right? Because 0 minus anything is going to be that same number. Basically, it's just a way to release energy. And then often it occurs with other types of radiation. So a lot of times if you have an alpha emission, you're also going to have a gamma emission. So often occurs with alpha or beta decay. We could do an example, but really you're just going to, like I'll just write that carbon 14 one, right? If I was to emit a gamma particle we go to balance it, sorry, that's a 6. I just get the same thing. It just has less energy over here. It gave off some energy. Again, that's usually happening also with, you know, alpha or beta decay. I'm just going to erase it because it looks weird. You rarely have it on its own. You can, it is possible, but usually it's in conjunction with something else. Our next one is positron emission. Positron is a particle. We normally don't say positron particle because the word positron kind of assumes particle in the name. It's kind of weird. So just positron emission or positron decay, those terms work for us. And then our symbol for a positron is actually going to be that beta symbol again, but with a positive charge. Now, be careful here. This can get kind of confusing. Like if we were to just say X, just regular, just it doesn't matter what it is, we assume that it's positive, right? So just an X and a positive X are assumed to be the same thing. If I wanted it to be negative, I would have to put the negative in front of it. This is not the same, so just be careful. If I'm writing a positron, I'm going to put that positive charge there. If I scroll back up, if I don't put the positive charge there, it's actually the negative version. So a beta particle is either just the beta symbol or beta negative. These two things mean the same thing. The positive version is a positron. It's different. So just be really careful with that. That can be kind of confusing at first. So a positron has the same mass as an electron, but has the opposite sign. So electrons have a negative sign, positrons are opposite to that, so they're going to have a positive sign. So beta positive. And where we're getting this from is one of our protons in our nucleus is actually going to decay into a neutron plus a positron. So a proton in the nucleus decays or is converted, however you want to say it, a neutron and a positron. And then of course positrons have no business being in the nucleus, so it's ejected. So the positron So looking at that little reaction, right, I'm going to have a proton. Again, I'm going to put a 1 for my mass number, a 1 for my atomic number. It's ejecting a positron, which I'm going to draw similarly to how we would draw that electron. So when we were to do our beta particle, right, I put a 0 for where the mass number is, and then a -1 because it would have a -1 charge, right? The charge on my electron is opposite to that of a proton. Here, the mass number is the same, so I still have the 0, but I'm going to have a +1 here because the charge is opposite to that of electron. And then I'm going to have my neutron as my other particle. So this here, right, this is my positron with the positive sign. Remember, if you don't put the positive sign there, you're talking about the negatively charged version, right? You're talking about an electron that's ejected from the nucleus. So be careful for that. When we eject a positron from our nucleus, from our isotope, our mass number is going to be unchanged, right? I'm taking a proton, which contributes to my mass number. I'm converting it to a neutron, which also converts which is also contributes to my mass number. So I'm like losing one, but I'm gaining one. So my mass number doesn't change. But my atomic number is going to decrease because protons are part of my atomic number and neutrons aren't. So when an isotope, when a nucleus, however you want to say it, ejects a positron or undergoes positron emission, that might be the better way to say it. You could say positron decay. The mass number remains unchanged. And the atomic number decreases by 1. So an example for this one, I'm going to have potassium 40. And again, I'm often going to give it to you just like this. So you're going to look on the periodic table, you're going to find potassium, you're going to see that its atomic number is 19, and then write that down. And then it's undergoing positron emission. So I'm going to write my symbol for a positron. And then again, we need to determine what our new isotope is, our new nucleus. So the sum of our mass numbers must be the same. So since I have a 1 here, for it to add up to 19, I have to have an 18 here, right? 1 plus 18 is equal to 19. I'm going to find 18 on the periodic table. That corresponds to argon, so I'm going to write down that atomic symbol. And then 40 minus 0 is going to be 40. So this would be my balanced nuclear equation for a positron emission. And then one more type for us. And this one is the first one where we're actually going to be adding a particle to it instead of emitting it. So this one is called Electron Capture. And it's really as it sounds. We're actually going to capture an inner shell electron. And a lot of times we'll just use a capital E and a capital N. Actually, capital C, that's electronegativity, capital E and a capital C for electron capture. I don't know where that N came from. Sorry about that. So what we're doing here is we're actually going to capture an inner shell electron. So a proton in the nucleus is going to combine with that electron. When that happens, it's going to convert a proton into a neutron. So our atomic number is going to go smaller because a proton's converted to a neutron. So we're losing one thing that contributes to my atomic number, but my mass number remains the same. So a proton captures, I think that always sounds funny, an inner shell electron. This type is not very common. And then this converts a proton into a neutron. So if we were to write this, kind of my symbol for electron capture, it's going to be the same symbol that I used for a beta particle because it's an electron. It's just that it's going to be on the reactant side. And we'll do a balanced example, but I have a proton combining with that electron and I'm producing a neutron. So we're gaining a neutron, my mass number is not going to change. We're losing a proton, my atomic number is going to go down by 1. So the mass number does not change. And the atomic number decreases by 1. And again, just have to be really careful. Electron capture, we're going to use the same symbol that we use for a beta particle. It's just going to be on the reactant side. We're actually absorbing radiation, not emitting it. So an example for this one, I have mercury 197. And again, we'd find mercury on the periodic table, its atomic number is 80. And then kind of the directions would say, write the balanced chemical equation when, you know, for the electron capture or something like that of mercury 197. So I'm going to capture an electron, which means I'm going to put it on the reactant side this time. And then the same sort of idea to get my product, right, to get my new isotope, we need sum of atomic numbers. So if this is an 80 and this is a -1, I'm going to have a 79 over here. We're going to find 79 on the periodic table. Gold is that one. 197 plus a 0 is a 197. So my balanced chemical equation for this one. So let's just do a real quick, just kind of review here, right? We had our alpha particle, and our symbol for that was essentially the nucleus of helium. We said if you wanted, you could write it this way. We had beta, and our symbol for this one, or if you wanted, with the -1. We have positron, so beta with a positive sign. Our symbol for that is essentially our electron symbol again. The mass is the same, but then it's a positive charge instead. So even though I'm putting an E here, it's not an electron, it's a positron, right? The electron has a negative. I guess technically you could do this and that would work also. Again, just be careful. We know that this is a positron this time because this is a +1 here and not a -1, right? If you didn't have that positive sign here, we still know it's a positron because it's negative for our beta. Again, if we're just writing this, the abbreviation for the type of radiation though, you don't have the negative there. And then what are we missing? Gamma. Gamma was the one that we said was just electromagnetic radiation, right? This one was not a particle. If we wanted, we would just put a 0 and a 0 here. It might be worth reminding yourself that this is not a particle. And then electron capture, we're going to have the same symbol as we did for beta, but this time, this is an important note, it's going to go on the reactant side. Maybe I'm trying to think of a better way to like make our little cheat sheet here. It's not really a cheat sheet, but our review here. Let's say we're going to add it. And then let's add, just we have it all in one spot. Sometimes we need our symbol for our neutron. So that's going to be an N for neutron, and then a 1 and a 0, and then our symbol for a proton is a P for proton, and then a 1 for both of those. So types of radiation. Just a couple more examples, and I want you to do these ones on your own. So you're going to write the balanced nuclear reaction for the following. So the first one, let's do beta decay of magnesium 28. And then the second one, let's do positron emission of xenon 118. So just, I didn't really review this part, but if you see it written this way, this number is the mass number. So magnesium 28 or the 28 as a superscript. Those do mean the same thing. So if you want to hit pause, that would be a good idea. Write these yourself, right? Here's our little list. You'll need your periodic table, and then when you're ready to check your work, just hit play again. All right, hopefully you guys did that. So magnesium 28, I do need my atomic number. So on the periodic table, when I look that up, I get a 12. It's emitting a beta particle. My symbol for a beta particle is this, right? Remember, a beta particle is an electron that's being ejected from the nucleus when a neutron decays into a proton plus an electron. And then to get my other isotope, we just need to remember that the sum of atomic numbers needs to be the same on both sides. So I need a 13 here, because 13 plus a -1 is a 12. That also makes sense because remember, a neutron is being converted into a proton, so my atomic numbers should be going up. We look on the periodic table, we find that 13 belongs to aluminum, or that aluminum has 13 protons, and then 28, because my mass number didn't change, right? Other one, xenon 118. Again, find its atomic number on the periodic table, which is 54. It's emitting a positron. My symbol for a positron is the E, but a positive one, right? Basically, it's a positively charged electron. And then I need to have a 53 here, right? Because a 53 and a 1 is a 54. Also, that makes sense because we get a positron when a proton decays into a neutron. So we're losing a proton. My atomic number should be going down by 1. I look on the periodic table, I find that 53 belongs to iodide, and then 118 for my mass number, right? My proton is turning into a neutron, so the total number of particles in my nucleus has not changed. That's still 118.